So today, I want to start with general relativity and basically give you a first look at cosmology. So how many of you know about general relativity? You can just put up your thumbs up if you have heard about it. What is the difference between general relativity and special relativity? So that's what the first thing I want to cover and tell you a little bit about how it comes about. So this is general relativity. At this point, I have it's a PowerPoint, but it's just to write notes in it. So if you see something in the chat and I don't see it, just let me know. Because let's see, this might be, I'm trying to make sure that I have all the windows open. Let's see. I do that, okay. All right, so let's do it this way. All right, so speak up if you have any questions, okay? Or just type them on the chat. There we go. And I have all the things ready. So what you know about special relativity comes out because Einstein said as a postulate that the speed of light is the same in all frames. So special relativity tells us about the speed of light being the same everywhere. And then he comes out and writes this very important work that was happening in 1905. But if you remember something that we talked about in special relativity, the assumption is always that one of the, for instance, that two people are traveling, they're not accelerating, they're just traveling at a constant speed. So there's no acceleration in special relativity. And it took him about 10 years. So from 1905 to 1915, Einstein is working on this idea of how do you implement acceleration into it. And in fact, this is called general relativity because the special theory of relativity is that a special case where there's no acceleration in the system. But now, what he's thinking about is we have this simple postulate, and we're gonna have now that acceleration. How do we incorporate acceleration into the theory? And he comes up with this general relativity. So let me go back a little bit and tell you about, let's see, where's my mouse? All right, got it. Somehow this is stuck. All right. So let's see. My mouse for the writing tablet is not behaving. So give me 1 second to fix this. All right, so now it's behaving. So here's the idea. Back with Newton, right? We saw in introductory physics, guys saw this in last year. We had that the force of gravity is given by some gravitational constant, the mass of the Earth, divided by the distance to the radius of the Earth times the mass of the object that we're looking at. And when you're near the surface of the Earth, we found that once you put in those constants, I mean, the mass of the Earth doesn't change, the gravitational constant g doesn't change, and the radius from the Earth at the surface doesn't change by much. If you do that, you get that famous 9.8 meters over second squared. So this is from introductory mechanics. You have the second law of motion too that says F is equal to ma. And so second law, right, F is equal to ma, which can basically be said to be the acceleration. Now let's make it a vector, is equal to all of the forces acting on the object, so the net forces divided by the mass. So that's the acceleration of the object of mass m. So we have the mass of the object on both ends, and we have that the acceleration and the acceleration due to gravity, they rely on this mass. But how do we know, and then this mass right here, let me highlight it. How do we know that this mass here and this mass are the same? How come that's the case and it's not maybe that we have this is the mass of gravity, right? And this is the mass due to the inertia of the object, how hard it is to move. So this is something that Einstein was thinking about. And you guys have seen this because on a special relativity, the object's mass is not the same as the how hard, because if it's moving fast enough, right? How hard does it have to move so that it's not, so that the change happens on its motion. So one was inertia and the other one was mass. So this is the question. The first question was, one is due to gravity and the other one is not. Are they the same? Does that make sense? Oh, sorry. Here I should have this 9.8 is the acceleration, but then there should be times the mass, that's the force, right? So this would be the mass of gravity. So how do we know that the two are the same? So this is one of the first questions that Einstein was asking when he was doing this. Any questions so far? Does that make sense at this point? All right, so one example would be, how about we take one and compare it to the other one. So let's say that what happens to an object that is dropped, you have it at shoulder width right here, and then you let it just drop to the floor, right? So what is the acceleration of this object? Well, we know that the acceleration is going to be related to this 9.8, that is this combination of constants, the mass of the object, gravitational mass, because there's a gravitational force acting on it. And then this gets divided, because we're using the second formula on the bottom, by the inertial mass of the object. So we could rewrite this as 9.8, then the units, and then we have to figure out if mg divided by mi is equal to 1. What happens if they were different properties? Then that would mean that the mg and the inertial mass are not the same. I mean, there's no reason for them to be the same at this point. But it has been looked at, and it turns out that people have done experiments where they look at this ratio, and it turns out that so if you do an experiment, I'll tell you a little bit about it, and you look at the difference between this number and 1, experimentally, what you end up with is about 10 to the negative 12. So it's not 0, right? It's not completely 0, but it's very close to 0. In fact, it's such a small number that people agree that this is exactly the same between the two. Questions? All right, so then the experiment, what they do is that they hang, let me see if I can draw it. So let's imagine that you have a rod right here, and then you hang from it a system with 2 balls attached to it in this direction and in this direction. And then you have in the same system another rod and then 2 balls attached to it this direction and this direction. And then basically they put them together. They're hanging from some roof or something. And then you want to see how the deviations are. So for instance, if you give a push to this one in this direction, this mass and this mass start rotating in this direction, how much do this guy gets affected right here? So if I push this one a little bit this way, how much would, first thing you have to know, this is the gravitational attraction between this object and this object, right? So if you move this one a little bit this way, how much would this one move in that direction? So yeah, this rod is firm, this rod is firm, and the only thing is that there's connected to that rod on the top, to that thing that is not moving, they're connected to something that can twist. So you can think of it as yarn back in the 1700s when they started doing experiments like this. And now you could probably use some really good wire to have the tension there. So there's a tension that forms that balances out the attraction between them because they're attracted to each other, but you're also putting some torsion onto that string that you have hanging from them. And that torsion is going to balance it out. And therefore, they're not completely going to go into each other through the forces of attraction, but you can see how they're attracted from the force of gravity. So we have this one, let's call it M1, M1 right here, and this one is M2. You would have that the attraction between these two is M1, M2 divided by the distance between them squared. And you also have a force of attraction between these two guys. But if you push them in one direction, then the distance here, we can call this one R, and then this one R prime. And if you push the first ones over here, this one, M1 and M2, then R is going to be less than R prime, and therefore this force is winning compared to this force. No, wait, hold on. No, they're actually the same. Sorry, that doesn't make sense. My bad. So yeah, that distance is going to be the same, right? Because if you push these two together, you're also pushing these two together. Does that make sense? All right, so experiments have been done on this kind of experiment, on this kind of setup, and other types of experiments have been popping out. So right now we know that the gravitational and inertial masses are almost exactly the same. And the error is about 10 to the negative 12, where it's not 1 exactly. But maybe there's another universe where mg over mi is actually 1.1, right? Or another number close enough to it, but not exactly the same. then that would mean that those two are not exactly the same, and that inertial mass and gravitational mass are not exactly the same. All right, so that's the first thing that I wanted to cover. So this is the idea that one of the first ideas that Einstein had to look at, and then he was coming up with thought experiments, and other people were doing real experiments where they're saying like, yeah, they're the same. We cannot measure a difference between them. Right. So the MI is the inertial mass. So for instance, if I have something and I push it with a force, I'm going to get it accelerated, and the acceleration is going to be related to that inertial mass. Now, if you're on the surface of the earth, the acceleration that you feel pushing you down, pulling you down, the force of gravity pulling you down is related to your gravitational mass. So now let's say that you were wearing um, um, yeah, let's say you were wearing skis or roller skates, right? So let's say you're wearing skis and you're downhill on the snow. A little bit of a push would result in a higher acceleration. So that's because you're not your real inertial mass, but how hard it is to push you. That's your inertia that you have. How hard it is to push you downhill because you're on skis on the snow is different than if I wanted to push you and just push you across the ground. So how hard it is related to this inertial mass. However, this inertial mass, what we're thinking about is in the gravity, force of gravity kind of system, like if you had an object being pulled down by gravity, right? Versus you're fighting gravity, the mass of the object. The inertial mass is how much you have to push on it. And then the other one is the gravitational mass. So they're, to this point, yeah, exactly. At this point, we know that they're exactly the same, but they don't need to be exactly the same. And that's the point that Einstein had to come up with and realize himself. So basically, if you were traveling at high speeds, inertia and mass are not exactly the same. But at this point, it's not, this is still mass, right? Like your inertia is something else that we talked about in special relativity. But your gravitational mass and your mass from just being mass are exactly the same. That's something that Einstein had to think about and say like, yeah, they're exactly the same. But they don't need to be. And experimentally, they have been proven to be exactly the same. And there's no reason that this doesn't happen. But this is not in our universe. Maybe another universe somewhere else. Is that clear? All right. So let me talk about another experiment due to Einstein, right? Let's say that you were put in a box. So there's a box. This is a person just near the box. In this system, um, you're basically on Earth, right here. So you would have that there's a normal force pushing on this person up. And this normal force is equal to the gravitational force. The gravitational acceleration is that, so you're standing up on the box and then you like normal, right? And you just feel a pull down. That's due to gravity. So let me say that G is in this direction here. And you're not moving because there's a force pulling on down on you right here, which is this exact same and counteracts this, the force of gravity pushing on you right now. And it's exactly the same as this normal force that is pushing up. So in this case, you have that. And then let's say that there was another person, they're in the box too, and this is the same size box and everything. There's no windows to look outside. And this person is actually in a rocket. So this is a rocket. The rocket is traveling with a force in that direction due to the boosters. And basically, in this rocket, there's an acceleration in this direction. The acceleration is g, that 9.8 that we were talking about before. And this person is also going to feel a force normal to them inside of this box on the floor of the box, where this normal force acts also, in this case, is the inertial mass times the acceleration, but we know that this acceleration is g, and this force of gravity, I mean, this mass, the gravitational mass is the same as your inertial mass, so they are the same. So this is the idea that Einstein had. He said, let's say that the floor is pushing upward on the first case when you're on the box and you're on the surface of Earth. And then on the second case, case B, you're inside of a rocket, but you're also in a box, so you don't know what's outside of you. And the rocket is moving with an acceleration g in the up direction with respect to the box. The questions for you would be, would you be able to tell the difference between those two? All right, so there's a poll. All right, so the poll says that 56% of you agree that you say that you can tell the difference. So how could you tell the difference at this point? Anybody? So anybody, can you tell me what your thinking is behind that you can tell the difference whether you're inside the rocket traveling with acceleration g, or you're in the box outside of your house? So let's see, John, what did you pick? John? All right, so then the question from Sivan, is the man in the rocket subject to gravitational pull as well? No, they would just be in space, right? Traveling in space. The only force acting on them is the normal force pushing up on them, and then they feel that. So John, which one did you pick? Same or not the same?
I put that they were the same, but I'm just kind of confused if that, I don't.
Okay, so you picked they were the same, that you wouldn't be able to tell, right?
Yeah, I said that you wouldn't be able to tell, but
All right.
I'm kind of confused.
Okay. So that's the right answer, right? Because you're feeling the force of gravity pulling on down when you're on the surface of the Earth, but if you were in the rocket and the rocket is moving with that acceleration of g in that direction, you would also feel the same gravitational force, but it's actually not a gravitational force, right? It's just acceleration moving you through space. So that's the point about it. So now we see that some people are saying they said no too, so that works out. The idea then is that gravity and accelerating frames are exactly the same. If you're inside of a box, this is a thought experiment that Einstein came up and said that it was the elevator, thinking that an elevator in space or an elevator that is not moving, and you wouldn't be able to tell between the two. And if this person had an apple right here and was going to drop the apple down, so here's their apple, he would be exactly the same as he lets go from the shoulder. He would behave the same way as an apple that was in his hand and this person accelerating and then just drop down. So when you see people in the, let's say in the space station, and they're actually having things and they're floating around, why is there a reason that things are floating around when they're in the space station? Anybody? They're inside a rocket, right? Well, the space station is not a rocket, it's more like a satellite. But why is it that once you get to space, you see that things start to float?
Because you're in orbit.
Because you're in orbit and you're in free fall, right? So there's no force of gravity. Well, there's a force of gravity, but the gravity is basically that you're falling towards the earth and missing it all the time. So you're in orbit and you don't feel the actual gravitational force, but the whole spaceship is going in that direction. In fact, if you go into that airplane, there's an airplane that goes up and then it goes down in free fall. And for about 30 seconds, you feel like if you were in space with no acceleration around you. And it's just because the airplane, it's indeed accelerating and is falling towards the earth, but because that falling happens to be in free fall, then you don't feel gravity around you. So they use it to train astronauts and other people around it. For instance, if you might have seen pictures of Stephen Hawking when he was put in into that airplane to do that. So I don't know if you guys have seen those. In fact, now let's say that you were in an elevator, right? And the elevator was in a free falling frame. So that means that, unlucky for you, you're in the elevator and the wires got caught and that elevator is going pretty fast down. It doesn't have any brakes on it. I mean, usually elevators, if the wires get caught, they put brakes and stop themselves from falling super fast. But let's say that you were in a box or an elevator, and then this elevator was just on free fall. What would be the forces that you feel? Well, in this case, you're basically in an inertial frame and it's the rocket with the engine off. And you wouldn't be able to tell the difference if you're in an elevator on free fall and kind of like that. I think it's called the barf airplane because some people, when they're in this no gravity state, they cannot handle it. And you're in this free fall state. That's exactly the same as if the rocket had been turned off, the engine is off, there's no push on it, there's no acceleration, and you would be just floating, and you can see that when people are in the space station. Okay? So what this tells us is that, and this is what Einstein came up with and called it the principle of equivalence. And it's just as strong as the principle of equivalence is kind of like the rule that guides general relativity out. And this is what took him a while to do, aside from the math that is pretty hard too. But It's kind of like how everything falls down in a special relativity. Once you have as a principle that the speed of light is the maximum speed and is the same for all observers. So that's the key for special relativity. This principle of equivalence is the key for general relativity. And what it says is that the form of each physical law is the same in all locally inertial frames. So that's what this principle of equivalence is. But it's basically that there's no way to tell if you're inside the elevator in free fall or you're inside the elevator that is inside of a spaceship in space with no acceleration acting on them. Or on the other case, if you're in the box and the box is not moving on the surface of the earth, or you're in a box and you're going inside of a rocket with acceleration g, you wouldn't be able to tell the difference. All right, any questions about this? So if there's no questions, let me follow up with this principle of equivalence and tell you about one effect of this principle. So one of the aspects here is, let's say that you had, let me see if I can draw this. Let's say that we had a rocket right here. It's gonna be a huge rocket, so let me put it there. There's the rocket. These are the little wings for it. It's accelerating, so there's fire under it right here. And then this is a really tall rocket. It goes all the way over here. And then we're gonna have a source of light right here. So here's a source of light. And the light is there. And then you're gonna have that there's an observer over here. So at this point, there's a person, and this person is able to look at the object down there. So they're able to look down. And there's a distance between the source and the object. Let's call it h for height. All right, so here's the first question. At t is equal to 0, the light is turned on. So this is an accelerating frame, right? All of this is accelerating. Let's assume that this is accelerating in this direction with acceleration g for it, the same as gravity, so that the person doesn't feel, if it's going too fast, then it's higher than gravity and you wouldn't like it. That's what we're assuming here. So what we know then is that the height of the distance between them is h. So how much time, let's say that at B is when light reaches the observer. So what we have to figure out is how much distance is traveled, right? And we know that the time is gonna be the same as the distance traveled divided by the velocity. This is light, so we can assume the speed of light right here. Questions so far? Okay, so now another thing that we know is that there's actually that the rocket is moving. And we know that at this time, the velocity of the rocket is gonna be the acceleration over the time that this rocket was moving, right? Between the light hitting the person at time t and time 0 is the time when the light was turned on. So it took a couple of instants of time, but it took some time. And it depends on whatever the height it is. So we know that the acceleration is g, and we know that the time was h over c. So now we can talk about what the velocity of the rocket was during this interval, and we can say that. Questions at this point? All right, so then this is the new part that you guys might not have seen yet. The other thing is that, and you remember this from a previous discussion that we had, if you have a wave expanding in one direction, right? But then so in this case, the wave is going in this direction. And can you guys see my mouse when I move it right there? So the wave is moving in this direction, and the person is there to observe it. So what happened is that there's a shift, a Doppler shift in the frequency of this. So it's kind of like when the ambulance is coming at you versus when it's going away from you. So you should be able to perceive a shift on the frequency. And if we know that this light is a particular frequency, this source of light over here, the person seeing it, because of this change in velocity that is happening, is going to actually see a shift in that frequency. This Doppler shift in the frequency can be calculated. And if we do that, we have, and I'm going to put the equations here. So this is the frequency observed by the person. It's going to be equal to the frequency of the light source. And then you have to do this 1 minus BC, that's the speed of the rocket, and the speed of the wavefront, 1 plus BC, a square root of that. So basically, if you do that, you can do some algebra. This is the same as f source right here, the square root of 1 minus b over c times the square root, no, sorry. Yeah, let me rewrite this. Divided by the square root of 1 plus bc. We can continue doing some algebra. Things cancel out. And actually, you use a Taylor expansion. I'm sure you guys have done Taylor expansions, right? So this is, so if you have 1 minus x to the 1/2 you can write that out. And in this case, we have this right here. And then on the bottom, we have 1 plus x to the negative 1/2, right? So in both cases, we will have the 1 minus 1/2 x, and then other terms right here. And in this case, when we're doing this part, we will have 1, and then we bring this 1/2 down, and we have 1 negative half x plus other terms that go there. So if we do that Taylor expansion of these two terms right here, and we get 1 minus 1/2 b over c, and then the other one is also 1 minus 1/2 b over c. And we can simplify this to just the source has a change in frequency that is related to 1 minus bc. So it was a lot of math, but it's just to show you that the observed frequency is going to get shifted depending on the velocity that the rocket is traveling at. Any questions up to there? All right, so then let me do the last thing I wanted to do. Going back to the principle of equivalence that we have talked about, right? Here, there's a person in a rocket, there's light, and then there's a frequency shift because of the rocket. So,
Sir?
yeah, go ahead.
Why is 1 minus half VC squared proportional to 1 minus V over C?
Oh, so this I'm just, so yeah, good question. So this, what I'm doing is the following. If I multiply this one and this one, I get 1, right? And then if I multiply this one, if I multiply this term and this term, I get negative 1/2, right? So then I multiply this.
What about the 1/4
and
V
this
over
one?
C squared?
Yeah, so I was gonna get to that. And then I get another 1/2. So I have the 1 minus BC. And then if you look at this number, the next one would be multiplying this one and this one. So that will give you a 1/4, but then you have velocity squared, the speed of light squared. And since the speed of light is on the bottom and it's a huge number, that goes to 0. So that's why I put it with this, not exactly equal, but it's just like the first term. The other ones are gonna get smaller and smaller. So this one is 1. This one is gonna be smaller than 1. And then you have, yeah, exactly, you have a plus 1/4 b squared over c squared. But this one is getting smaller and smaller, right? We still have, and this is the Taylor expansion, so you're gonna have more terms, but I'm just saying, okay, I just need the first one and then cut the other ones out.
But if we are in relativity, don't we assume that the velocities are very high and that V over C is not negligible?
It's not negligible, but it's still smaller than the other ones. So yeah, you can do the expansion like that and just keep going. And your shift is gonna be shifted basically it's just, I'm just trying to get like the first order estimate. But if you keep going, you will have the next correction and the next correction. So basically your first correction, let's say was 1/2. Your next correction is gonna be 1/10, changing it to 1 by 1/10 or so. Does that make sense? I'm just cutting it off because I don't want to do the whole math.
Okay.
All right. So now for this idea, the question is, if we have that this rocket is moving and all of that, and we see a frequency shift, this is the first idea. Oops, I did something. No. This is the first idea to think about. This is the idea of the light source being down here and you have the observer in the rocket, right? So that means that if you have a source of gravity and you have a light source in it, right? So now let's think about it this way. This is our Earth. Here's a light source right here that is sending light out. Okay. And then the frequency of this light is going to be changing exactly the same because there's a gravitational pull and it's equal to the acceleration. So this light, it has a particular frequency, but somebody that was over here is gonna see a different frequency. And that shift in frequency, this person is not being affected by gravity, he's just orbiting the planet. He's gonna see a different frequency than the source. And it's just like being in the rocket because of the equivalence principle. Does that make sense? So this is a key part, okay? That means that the light beam wavelength is gonna be growing if the frequency is decreasing as you change. So if you have an object on Earth, G is the acceleration. But let's say you had an object that was in the sun, then the gravity of the sun is way higher, right? So the light coming out of the sun is being shifted and is getting slower because gravity is pulling it down. And can you make an object that was so massive that its gravity was so big that the gravity of that object was going to change the frequency here, right? This acceleration is now super high so that the light is basically frozen because it's lower and lower in frequency until it cannot even escape the object. Does that make sense? Arthur? What would you call that object? Light cannot escape from it.
That would be a black hole.
Exactly. So that's the idea of black hole. So this is one of the things that I wanted to cover, like how is it coming out, right? And I think I ran out of time. But if you have questions, I'll be happy to answer your questions in the room. Otherwise, you're free to go. This is the main thing though, that how gravity can stop light from leaving an object. You have to be a really massive object, but that can happen. All right. Do we have any other questions? No? All right. I'll see you guys around. Thank you.